In addition to the IMC method and the direct synthesis method, there are a variety of published tuning relations. Our textbook next introduces integral error methods and the AMIGO method. The integral error methods are based on minimizing the total error. Popular criteria for developing integral error methods include the integral of the absolute error, the integral of the squared error, and the integral of the time-weighted absolute error. The integral of the squared error method can result in the most aggressive controller tuning settings, whereas the integral of the time-weighted absolute error results in the most conservative settings. The formulas required to calculate both PI and PID controller settings for the ITAE method, either for disturbance or set point inputs, for an FOPTD model, are provided in Table 12.4 of our text. While these integral error methods are based on minimizing the error of a controlled variable, they are not developed to consider robustness. On the other hand, the AMIGO method is developed with an objective of rejecting disturbances and maintaining robustness of the process. The AMIGO method is an acronym that stands for the Approximate M-Constrained Integral Gain Optimization, and it's based on an expanded form of the PID controller, where there is a gain for the proportional element, a gain for the integral element, and a gain for the derivative element. The derivative element of this expanded form of the controller transfer function is based on only the measured value, so it eliminates kick. The AMIGO method was designed by compiling optimized results for over 100 different transfer functions, representing 10 different transfer function types, and then developing equations describing either the PI or the PID controller settings. These are in tables 12.5 and 12.6 of our textbook for FOPTD and integral plus time delay models. Unlike the direct synthesis and IMC methods, the AMIGO and ITAE methods do not have an adjustable parameter like tau c. Some general guidelines for selecting the controller tuning settings that can be derived from all of these methods are proposed here. In general, the controller gain should be inversely proportional to the product of the valve, process, and measurement gains. So if one of these other gains increases, the controller gain should be decreased. Large values of time delays, or large values of the time delay relative to the dominant time constant in the process, tau, make control difficult and should require the use of smaller values of the controller gain. Both the derivative time and the reset time should be increased as theta over tau increases. When PID control is used, in general, the ratio of the derivative time to the reset time should be between about 0.1 and 0.5. If integral control is added to a proportional only controller, then the controller gain should be decreased, and if derivative control is added to a PI controller, then the controller gain can be increased, because adding the derivative control can help to stabilize the controller. An example comparing controller tuning settings for an FOPTD model that are calculated using the IMC method, the AMIGO method, the ITAE method, and a method that we have not yet introduced called the Ziegler-Nichols method is shown in example 12.7. The response of this FOPTD model to both a set point step input and a disturbance step input are shown here. Note that for the unit step input for the set point, all four of these PI controllers bring the process to a final steady state consistent with the step set point change. At a later time, a step disturbance is introduced, and the objective is to reject that disturbance so that the controlled variable y should come back to its steady state value before the disturbance. Using the IMC settings, with a tau c equal to 1, results in a gain of 0.5 and a reset time of 1. The AMIGO method predicts that the gain should be set to 0.25 and the reset time should be 1. The ITAE method uses a larger value of the gain, 0.86, and reset time, 1.48. And the Ziegler-Nichols method uses the largest value of the gain, 1.02, and the largest value of the reset time, 2.58. The Ziegler-Nichols controller tuning settings, introduced in section 12.5.1, are designed to result in a 1/4 decay ratio. As you can see here, after the set point change, the Ziegler-Nichols method results in oscillations, and those oscillations should decay so that successive oscillations are 1/4 of the height of the previous oscillation. This is a relatively aggressive controller tuning because it has a large value of the gain. The AMIGO method, on the other hand, has a very small value of the gain compared to these other methods and is therefore the most conservative controller setting. Remember that the AMIGO method is designed with robustness as an important criteria. So the AMIGO method is more likely to be able to tolerate changes in the process without becoming unstable. But as you can see in this comparison, that makes the AMIGO method slower to respond to set point changes and slower to reject disturbances compared to the other methods. Although these controller tuning relations are tabulated for simple process models, such as FOPTD and SOPTD models, or integrator plus time delay models, they can also be used for much more complicated models. For example, from our textbook, in example 12.8, we have a process model that is 4th order in the denominator and includes a time delay. In order to use our controller tuning relations, we need to approximate G using a much simpler function. And you know how to write this as an FOPTD model. Once we have an FOPTD approximation for G, we can find appropriate controller settings using any of the methods we've introduced. Here, we use the IMC method, the AMIGO method, the Ziegler-Nichols method, and the Skogestad modification of the IMC method. And again, just like in example 12.7, we test the response to both a unit step input in the set point, and then at a later time, after the set point change has settled down, a unit step disturbance input. Now, although we approximated this higher order transfer function as a lower order transfer function for the purpose of tuning the controllers, when we model the response is modeled using the full process transfer function and the controllers that were obtained using the approximation. Here, the IMC method was tuned with a tau c equal to 1, which is quite conservative because 1 is the largest time constant in the process. That relatively conservative selection for tau c results in minimal or no overshoot in response to set point changes, but relatively slow disturbance rejection compared to the other 3 tuning methods. The rather aggressive Ziegler-Nichols tuning method results in the expected oscillations that decay in response to set point changes, and the disturbance input also results in oscillations. The Skogestad modification of the IMC method results in a smaller value of tau I than the IMC tuning, and is therefore better at disturbance rejection than the IMC method. Remember that the AMIGO method is developed considering robustness of the process. So this one has the smallest value of the controller gain, but nonetheless still results in some overshoot in response to set point changes. In the next video, we'll introduce some online tuning methods, including the continuous cycling method.